Good day, I'm Dr. T. Welcome to my office. So today I'd like to talk about the wonderful world of waves. So waves are going to be energy traveling through a medium, unless it's light. Light gets weird. But waves are going to be energy traveling through a medium. So the classic would be like ocean waves or sound waves. We'll talk about light. I'm going to shove light to the end because it's weird. Okay, so let's talk ocean waves. So ocean waves go up and down as the wave goes across. This makes it a transverse wave. Transverse waves, we can categorize things by, hey, when it's going up and it's peaking towards the top, we'll call that the crest, and the bottom of the wave, we'll call that the trough. We can measure the distance from crest to crest or trough to trough. We'll call that the wavelength. Wavelength we give the Greek letter lambda to, and it's going to be measured in some kind of length unit. Likewise, we can measure how often the crest happens or how often the trough happens. So how often does it go up to up? And we call that frequency. The unit on frequency is going to be the hertz. That's 1 divided by seconds. And we give that the Greek letter nu, which kind of looks like a squiggly V. Now we can also measure the height of the crest or the depth of the trough, and we'll call that amplitude. Amplitude ends up being a fairly important feature for most transverse waves in that it tells us the energy of the wave. Note, light is weird. It has two different energies. But back to ocean waves. If you're ever listening to the shipping forecast, how high are the waves is one thing that will be covered. Low energy waves, remember energy does work, including breaking your boat. So low energy waves, low energy, your boat should be fine. Big, tall waves, lots of energy, maybe you don't want to be out on the ocean and or lake at that time. Sound is a longitudinal wave. This is basically 90 degrees difference. See, in the ocean wave, the particles, the water molecules, are more or less going up and down. They're not traveling with the wave. When the wave travels, the particles, unless it's light, don't travel with it. Instead, they wiggle up and down. So the medium, the thing the wave is going through, is made up of particles, atoms and molecules and the like. And in a transverse wave, they go perpendicular to the travel of the wave. In a longitudinal wave, they don't go with the wave, but they do move parallel. So they go back and forth. Sound is a longitudinal wave. Now, there are correlations pretty well with transverse waves and longitudinal waves. With longitudinal waves, we don't have troughs and crests. Instead, we have compression and refraction. Compression, the particles all squish together. Refraction, they push apart. If you look at a speaker, in particular a nice low frequency speaker, you can see it going back and forth, back and forth. Basically, it's compressing, refracting, making the sound that you're listening to. Wavelength is the same idea, compression to compression or refraction to refraction. And frequency, same idea, compression to compression, same deal as would be for a transverse wave. Amplitude is how much did you squish versus how much did you refract. Likewise, little squish, little energy, big squish, lots of energy, more like you are to break something, like your ears. Okay, I want to dive into several other topics with respect to waves, but to do so, I want to do a bit of an example. So I'm going to play an A4. This is the note A, and it's going to be the fourth A, 440 hertz for the frequency. And I'm going to play it as just a pure tone. Okay. Next up, I'm going to play it again, but this time I'm going to play it on a violin. Those did not sound the same, and I want to dive into why those two didn't sound the same by thinking about what's going on here. Okay, so the 440, that was just the tone. That was a computer file telling your computer to wiggle the speaker back 440 times a second. Fairly straightforward. Now, with the violin, eventually it turns into a computer file because, you're watching this on your phone or computer or whatnot. But I'm generating that not as a computer file that I downloaded from Wikipedia, but instead, I've actually got a violin there. And so if you look at what's going on, in my right hand, I'm holding a bow. In the left hand, I'm holding the violin. My bow is covered in rosin, which is basically dried tree sap. So it's a fancy stick with horsehair and some tree sap on it. The tree sap makes it a bit tacky, a bit sticky. So it's going to grab the string. And I'm playing this on the A string that's just an open A that hopefully I tuned to 440. At least that's kind of what my phone said. I think it was just a smidgen under. So I'm pulling that along, and what's going to happen is the string is being grabbed by the rosin and the horsehair, but it doesn't grab it very tightly. So it grabs and releases, grabs, release, grabs, release. And that's going to cause the string to wiggle back and forth in a transverse wave. Now, each time it does that, it's going to send the wave going in both directions, but you know, I'm pretty close to the bridge, pretty far from the fingerboard. So let's think of it going towards the fingerboard. It's going to go up towards the fingerboard, then it's going to bounce off and run back. It's going to bounce back and forth, back and forth, back and forth. Well, as one goes forward and comes back, the bow is creating another one. So two of them are going to run into each other. Now, one of two things can happen. If one is going up and the other is going up, or in this case, side to side, so they're both going the same direction, they're going to add to each other. This is called constructive interference. If, however, they are going to go in opposite directions, then I'm going to get what's called destructive interference. They're going to cancel themselves out. So only those waves that can go up, bounce off, and come back are going to experience constructive interference. This is what we call resonance. This is where we're taking some kind of cyclic action, like a wave going back and forth, and we're adding energy each cycle, making it stronger and more intense. Now, what allows the wave to go up and bounce off? Well, that's going to be the wavelength. So there's a fixed distance between the bridge and the fingerboard. I'm going to change that in the next time you see me play by sticking my fingers down, but that's just an open string. So that distance determines the wavelength, but we're talking frequency. So how do we go from wavelength to frequency? Well, if you've ever seen someone tune an instrument, in this case a violin, well, you'll notice there's these kind of pegs sitting off. There's actually 8 of them. 4 on one end past the fingerboard and 4 past the bridge. The 4 past the bridge, kind of closer to my face, those are for fine tuning. They're nice fine threads. The ones past the fingerboard, that's just a friction fit. That's a little bit more of the coarse tuning. And what they're going to do is you're going to tighten up or loosen up the strings. There's 2, one of each for each string. And so in order to tune it, I'm going to change the tension in the string. And of course, the strings have different thicknesses as well. This changes the speed of the wave that travels through the string. By adjusting the speed, and if I have a locked-in wavelength based on the distance between the bridge and the fingerboard, then that can control the frequency. Because for waves, speed equals frequency times wavelength. Okay, so I've now tuned my violin. At least, hopefully I did. I was using the cell phone. It's been 25 years since I was in orchestra. Oh, it's been so long. I can also change the frequency by leaving the speed constant, but changing the length of the string. This can be effectively done on a violin by pinching the string between my finger and the fingerboard, thereby preventing it from wiggling past my finger, effectively shortening the string. So I'm going to go ahead and play a few notes. On the downstroke, I'll do D, C, B, A, and then on the upstroke, I'll do A, B, C, D, and hopefully you can hear the difference of the slightly shorter string. Okay, so we're able to pick the frequencies that are going to line up with the wavelengths, and the wavelengths are going to be determined by kind of the gap. But I keep saying wavelength, shouldn't it be wavelength? Well, here's the difference between the computer-generated tone and the violin. See, multiple different waves can actually fit in that wavelength. I can have one that's going up all the way over and then down all the way back. Or I could have one that goes up, down, and then up, down. Where they cross and it doesn't really move, where if you were to strum the string and you would see it not really moving, that's called a node. And then the parts where it's really moving, you're getting trough crest, trough crest, trough crest. when you're creating this, what we call standing wave, or where you've created your resonance and the wave's just bouncing back and forth. Those are called antinodes. And so basically I just have to make sure my nodes line up, and well, there's multiple waves that can get those nodes to line up. These are what we call harmonics. My violin isn't just making 440, or slightly almost 440 hopefully. Instead, it's making a blend. The 440 is the one you hear, that's the longest wavelength, the lowest frequency, and that's what our ears typically pick up on, but there's other harmonics, other frequencies that are higher frequencies, shorter wavelengths that are being generated by the violin. Now, only some of them, because most of them are happening to have destructive interference, but that string is going to create several standing waves, all within it, based on constructive interference. Now, of course, you've got the body of the violin. That's an air gap. That's area for air to bounce back and forth and get constructive and destructive waves. And the size of that body is also going to determine which of those harmonics are further amplified or further have constructive interference, and which ones get more of a destructive interference. This is the general vibe for all musical instruments, including voice. If you think about your mouth and your throat, you've got your vocal cords. Those start the wiggling with the air, and then the rest of your mouth and head gives you different spots for different resonance to happen. And thus, depending on the size and shape of your mouth and head and whatnot, you're going to get different harmonics coming out. You don't make just one pure note. Now, let's do a couple of terminology things. That blend of harmonics, the way you're able to hear, like, oh, that sounds like a violin. Musicians are generally going to call that timbre or tone color. Kind of think about it, it makes sense. It's like the sound version of color. The frequency, our subjective experience of that, is going to be what we call pitch. And it conveniently goes with high frequency or low frequency. So high pitch, high frequency. That does not sound good. Low frequency, low pitch kind of scenario. And then the amplitude, the energy, is what we describe as volume. I should point out that we use decibels as a unit for volume. That's actually a log scale. Turns out with seeing and hearing humans, we tend to work almost on a logarithmic based system. So a little more to something that's quiet is quite significant. A little bit more to something that's already quite loud is indistinguishable. We can use this idea of constructive and destructive interference in other ways, not just musical instruments. A classic are going to be noise-canceling headphones. Now, you can do kind of passive-based ones. These basically just have foam. As the air is bouncing back and forth, it's wiggling the foam, and that's actually generating heat. So you're converting the pressure waves into heat. You're heating up the headphones just slightly. We're not talking all that much energy, and that kind of dampens out the sound. Or alternatively, you could actually use a computer, put a microphone to listen to the sound coming in, and then you could create a tone that would be the opposite. So as the sound that's coming in is compressing, that tone will be refracting, and the two will cancel each other out. And thus we can use destructive interference to create active noise canceling. It works quite well, although a piece of foam and just converting it to heat also works pretty good, to be honest. We are hearing frequency. As the sound goes in our ears, it wiggles our eardrum, wiggles the bones, wiggles the fluid in our inner ear, which wiggles little hairs, and that's how we hear. But quite often, wavelength is actually what's being produced, and this can get a little bit interesting if, say, we or the thing that is producing the wavelength is moving. And this is called the Doppler effect. So I'll do a quick little animation and example. And the example. Okay, so you get the idea. As you're coming towards something, the wavelengths are compressing because you're physically moving the sound source closer and closer, so you're chasing the waves, and thus they're going to have a lower frequency. They're going to hit in faster, so it's going to sound higher, and then as it's going away, you're kind of spacing them out more than what they were right as they're being created, and as such, it's going to sound lower. I've got students who live near one of our fire stations, and quite often they can say they can tell which way the fire trucks are going based on the sound of the fire trucks. Okay, let's move out of the wonderful world of sound, and let's go to earthquakes. Earthquakes have multiple different waves. So basically, deep down in the ground, you've got two big hunks of rock and they're moving, and of course they're shaking things up as they're slipping around. And so you're going to create a series of different waves. The first waves that are going to kind of be reaching you. So if the earthquake happens, they're all created at once. But if you're away from the earthquake, the first waves that reach you are called the primary waves, or the P waves. Now, a P stands for primary, but I like to think of them as pressure waves because they are longitudinal waves. And they happen to move the fastest. Thankfully, they don't do a lot of damage. But there's more coming. Next up are the secondary waves, or the S waves. I like to think of like sine waves because these are transverse waves. They're noticeably slower, but a bit more damaging. The damaging ones are going to be coming next. After that, you've got your surface waves, and these are going to be a little bit more on the transverse style. They get a little bit different because you're right at the surface, and these are where the damage actually happens. These are much, much more destructive than the other waves. The P waves, not too big of a deal. S waves, a deal. The surface waves, yeah, this is what breaks buildings. But there's an interesting feature here. Because the P waves are much faster than the S waves, which are a little bit faster than the surface waves, if you're reasonably far away, you can pick up the P waves, sound an alarm, and the time between when the P waves hit and the S and the surface waves hit might actually be enough that you could maybe do something with that alarm and get to some place a little bit safer than where you happen to have been. So this is one way of doing earthquake alarms. Now, of course, obviously, if you don't know where the earthquake is, this also helps you find the earthquake because you know how fast the different waves travel. And as such, well, you can calculate how far away the earthquake was. Do that from a couple of different seismometers and you can pinpoint where the earthquake happened. Okay, so we've got ourselves some earthquake waves. And I've been putting off light, haven't I? So let's jump into the wonderful world of light, where actually I have quite a bit to discuss. Light is a transverse wave. Well, it's not a transverse wave, it's actually two transverse waves. You've got an electric wave and a magnetic wave, and they're rotated 90 degrees. So if the electric wave is going up and down, the magnetic wave is going back and forth. They're both traveling in the same direction. Light is also packaged into little packets, little particles called photons, which allows it to go through a vacuum. This was actually one of those weird ideas. In the 19th century, we thought, okay, all waves go through a medium, light must go through a medium, so there must be a medium, we just haven't found it yet. We'll call it the luminescent ether, some like mysterious fluid that we can't see that permeates the entire universe. 1887, Michelson and Morley come up with this experiment where they try and measure the motion of the Earth through the ether. They find it's not moving, which either means the Earth is not moving or there is no ether. The Earth is moving, therefore there is no ether. And thus the weird, bizarre story of light, which actually leads us into things like quantum physics, begins. This doesn't make sense. So I'm going to try and explain light, but keep in mind, it definitely is a bit of a weird one. Okay, so when it comes to light, we've got the same basic properties, except for a rather interesting quirk when it comes to amplitude. When it comes to amplitude, we're dealing with both the energy in one little packet of light, as well as how many packets we have. So amplitude is going to be a description of how many packets of light we have, whereas the energy per photon, the little packet of light, well, that's actually not going to be related to the amplitude. Instead, that's going to be related to the frequency of the light times by Planck's constant. Now, this sounds like I'm splitting hairs. Why do I care about the total versus the individual packets? Well, it turns out if you want to do any chemical anything, generally speaking, that doesn't matter about the total amount of light you have. That instead depends on the amount of energy in a single photon, because you're going to be doing actions on a per photon basis. And thus the energy of the photon becomes the critical feature for whatever you're doing. This includes seeing. See, when we're observing the world, what we're doing is we've got specialized cells with modified molecules in them, variants on the chemical retinol, which we can get from things like beta-carotene and whatnot. And that is actually going to change shape when a photon of appropriate energy impacts it. That means that only photons with the appropriate amount of energy, which is proportional to frequency, and frequency, remember, is linked with wavelength, so all of these terms are pretty much interchangeable at this point. Only certain photons of specific energies are going to be able to interact with our eyes. That's why visible light is actually only a tiny, narrow part of the electromagnetic spectrum. We've got all kinds of different energy levels for our photons. They have different wavelengths, different frequencies, and we can only see a tiny little bit because only a tiny range of energies for those photons will interact with the molecules in our eyes. To make things even more interesting, we actually differentiate between some of the different energies in that visible light. So we have got rods and cones. The cones come in 3 flavors: a red, a green, and a blue. And they are able to detect, in the case of the red, photons on the lower range of what we're able to see. In the case of the blue, photons on the higher range of what we can see. In the case of the green, photons kind of in the middle, but slightly to the higher end of what we can see. By having red, green, and blue cones, we're now able to see color. So not only do we see that we have light, we get to see the amount of energy per photon, and we call that subjective experience color. And of course, that makes our world, much more rich. It gives us a lot of information about the things we see, all thanks to the amount of energy per photon. Now, the number of photons, that's brightness. Generally speaking, a rod or a cone isn't going to trigger on one photon. It needs at least a few, and the more it gets, the more it's going to trigger, and we're going to interpret that as brightness. Now, while we're onto the wonderful world of color, let's talk about primary colors, because this is one where a few people tend to have a few misconceptions. There's not 3 primary colors. There's 2 sets of 3, so there's 6 primary colors. The reason there are 2 sets of 3 is that we're doing additive and subtractive color. Okay, so let's look at the additive spectrum. And of course, good old RGB. The marketing companies for computer peripherals have definitely burned that into everyone's brain. So it's red, green, and blue. And that matches the cones in your eyes. And so you put red and green together, you get yellow. You put blue and green together, you get cyan. And you put blue and red together, you get magenta. And you put them all together and you get white. You change up the different ratios, you get the rest of the spectrum. Or I should say the rest of the color wheel. Because it turns out magenta, if you look at this guy, that's red and blue. Those are on opposite ends of the spectrum. That's basically the sides are intense, but the middle, the green, is missing. So magenta is like a color, but not a color. It's a color, but not a wavelength. It's not on the spectrum. Now, if we're doing subtractive color, this is a case where instead of emitting light, what we're going to do is we're going to reflect light, but we're not going to reflect all of it. We're going to use things like pigments and dyes to absorb some of the light, because remember, different energies are going to interact with chemicals differently. Or we can actually do weird physical interactions where we do constructive and destructive interference on light. If you see a thin film of oil on a surface, it's got that old rainbowy thing, you're seeing constructive and destructive interference on light. There's dozens of ways to make color. I'm only going to kind of cover a couple of the big ones. Okay, so subtractive. We're using something that's making some of the colors go away. So the primary colors are going to be yellow, magenta, and cyan. You're familiar with this if you've ever bought ink for an inkjet printer. You got the Y, the M, the C, and the K. The K is black. It's a carbon black. It's really good at just absorbing everything. Magenta is subtracting the green and leaving the other colors. Cyan is going to be subtracting the red, but leaving the green and the blue. And then yellow is going to be subtracting the blue and leaving the red and the green. So if I take magenta and yellow, mix them together, I'm going to subtract the green and the blue, I'm left with red. Cyan and magenta, well, I'm actually left with blue in that case. And cyan and yellow, and I'm left with green. By the way, this is one reason why artists really want a good cyan. You need a cyan, which is actually a surprisingly hard color to make from a chemical perspective. I do want to point out that the different frequencies of light and different wavelengths and the different colors, the colors is subjective experience. So generally speaking, we can say, well, a certain number is close to a certain color, everyone's experience of that color may be just slightly different because it is, once again, a subjective experience. Okay, let's talk optics. This is one of Newton's big inventions. So we're going to be going through lenses and mirrors in order to shape light. You can shape waves. Typically we're going to do this with light, but you can totally do this with sound and ocean waves, etc. But we're going to focus on light. Just keep in mind, the same principles do apply to other waves. Okay, so as light is traveling, if it's going through different mediums, just about any wave is going to be the same story. As it's going through a different medium, it's going to change speed. Now, if a wave interacts with a medium on an angle, it's going to change speeds and directions. We call that refraction. So if you are going, say, straight on from air to glass back to air, nothing really happens. But if that glass is at an angle, then you're going to start bending this. Or if, say, water or whatnot is at an angle, you're going to bend it proportional to the optical density. Basically, how much does it slow down the light as it's traveling through? Same happens with things like water and sound and whatnot. This is why your ears don't quite work well when you're underwater. Everything sounds weird because your ears are optimized for air hearing instead of water hearing, and how different temperature layers of water will scramble sounds. Submariners learn to hide underneath what's called the thermocline, which is a temperature differential. It makes it harder for sonar to find them because keep in mind the whole point of a military submarine is to hide. Okay, now for light we can use this to our advantage where we can make a curved piece of glass or crystal or whatever, and by doing so we're going to be able to direct our light, and we might very well be able to direct it where we want it to go. So if we have a convex, it's going to be fat in the middle and scrawny on the corners. So if we have a convex lens, that's going to take the light coming in and it's going to aim it into what we call a focal point. It's going to concentrate it on one spot. The opposite is going to happen if we have the opposite. The opposite of a convex lens is a concave lens. It's been caved in the middle. That's the way I think about it. So it's fat on the outside, skinny in the middle. And that's going to cause it to spread out. It's going to be very divergent. Now, mirrors, instead of the light going through, the light's going to bounce off. When a wave or just about anything bounces off of a surface, it's going to bounce off at an angle that's equal but opposite to what it hit with. So if it hits at 90 degrees, it's going to bounce off at 90 degrees. Yeah. But if it hits at 30 degrees one way, it's going to bounce off at 30 degrees going the other way. Well, if it's curved, you can kind of control the way those bounce. Now, with a mirror, they're going to act very much the opposite of how a lens would. So a concave mirror is going to create a focal point. You're going to take the light coming in, it's going to bounce off, and it's going to line up with a focal point. For a convex mirror, the light's going to hit in, it's going to then diverge. We can use these to our advantage. If you want a focal point, you're going to be converging things instead of having them diverge. If they're converging, that's going to make something look bigger and closer. If it's diverging, it's going to be broader. If you're walking through the hallway at some places, they'll have these like large curved mirrors that basically allows you to see around the corner so you don't actually run into someone. More places need those, by the way. Okay, so we have this. We can kind of use this in a couple of applications, one of which is eyes. In particular, those of us who are just a touch or more than a touch nearsighted. Let's put it this way. I can kind of tell there's a camera right now. Yeah. So, what's going on? I'm nearsighted, and what makes me nearsighted is that my eyeballs are too long. I know, weird way of thinking about it, but this appears to be fairly common for individuals who grew up and spend a lot of time looking at things relatively close, aka we spend a lot of time indoors. I spent a lot of time indoors as a kid. Most people do. And as such, the muscles controlling our eyes kind of don't develop quite right, and our eyeballs get too long. Well, your eyeballs have to have a lens in them, which is good, and that lens is a convex lens. It's going to be taking the light from outside and it's going to be focusing, and it needs to focus that light onto the back of your eye where the retina is, that's got all those rods and cones that are doing all the seeing stuff. And if it doesn't focus it particularly well, then light from slightly different spots are going to kind of be all over the place and everything's going to look all fuzzy. Believe me, I know what fuzzy looks like. Well, if your eyeball's too long, like mine, then it's going to focus it, but it's not going to focus it on the retina. It's going to focus it in front of the retina. And then it's going to be, once it focuses, it keeps on going, but it starts spreading out again. It doesn't just line up. We're not making a laser here. And so it's going to start spreading out, and thus it hits all over the spots, and it looks kind of fuzzy. So what I need to do is I need to have that focal point moved backwards. I need to get it further back to match where the actual retina is, because once again, my eyeballs are too long. I'm going to use the opposite of what I've got. I've got a convex lens that's making the focal point, so I want to actually make the lens not work as well. So I'm going to have the light diverged before it gets in there. And I can use a concave lens. Now, actual glasses lenses, these things are much more complex because what I'm currently describing would only work if you're just looking straight ahead. If you look up and down, it would be not quite right. So the complicated curve of glasses lenses gives you areas where you don't accidentally affect color, you don't get any weird rainbowing effects, and then you also can look in different directions. It all looks nice and clean. So in this case, we're going to do a concave lens in front. That's going to start diverging the light. Now the light's starting to diverge, so it's got more to be done in order to get it focused. And so the lens in my eye is going to focus it, but it can't focus it as well. So it's going to take a little bit farther, and it's going to focus further back, right where I want it to focus, because once again, my eyeball is too long. So we can use this to our advantage. I kind of alluded to something, this idea of rainbowing. So it turns out when a wave is going through a medium, if you've got a mixture of slightly different wavelengths and frequencies and energies, like, it's a polychromatic spectrum, you got more than just one color, sometimes they will slow down and take an angle at slightly different rates. This is how we get rainbows and how prisms work. So got a prism back there. Also got a painting of Stradivarius making a violin. So the way a prism works is as the white light's coming in, you've got yourself this triangular shape. It's called a prism or a triangular prism. And it starts spreading out the colors of light because the different colors bend at slightly different angles. Same thing happens with raindrops. So if you get yourself a raindrop, a rainbow is created by a double refraction through there. So it's going to be this internal reflection. The light's coming in, it's actually bouncing off the inside of the raindrop and then kind of arcing back. And so now you're going to get this kind of spread of light coming out of the raindrop. Now, a raindrop, a rainbow doesn't make. You need a bunch of them because as you're looking up in the sky, if your raindrop lines up so that it happens to be shining its red part of its light towards you, it doesn't look like a rainbow, it looks like a red spot in light. But if you have a bunch of raindrops, some of them will be lined up so it shines the red part of the light to your eye, and some of them will be lined up for the yellow and the green, and you get the rainbow with multiple raindrops all in slightly different orientations. And the angles of this is going to be locked in based on the angles that the light is bouncing around inside the raindrop. Side note, you can actually get a third fraction pretty easily, although not nearly as intensely, and that's how you get double rainbows. You actually always get a double rainbow, but usually you can't see the other rainbow. You'll get multiples of these, depending on how many bounces you actually get, but each one is less light going through each bounce, and thus, less bright. Okay, let's round things off with the classic question, why is the sky blue? There's another KXCD on this one. So the typical explanation is what's called Rayleigh scattering. Basically, if you've got a light wave and it's going and interacting with particles, or it's interacting with things that aren't actually its medium, so if you've got a wave and it's hitting an island or something, what happens kind of depends a little bit on what it's interacting with. So let's imagine just kind of a narrow slit. So if a wave's going through a narrow slit, it's going to kind of go through and it's going to spread out. And so a nice straight wave is going to start spreading out. If you have a couple of slits, you're going to spread out and you're going to get constructive and destructive interference patterns. Always an interesting approach. But if you've got little tiny things, so instead of like big islands with slits in between them, but you got little tiny things, you can start getting the light to scatter in different directions. It turns out oxygen and nitrogen molecules are roughly the same size as like blue light. And so as the light from the sun shines through the Earth's atmosphere, the blue light gets scattered a bit. The end result is that if you look up, not where the sun is, but where the light is just bouncing around the air, it's going to be blue. Now, if you were on the moon where there's no air and you look up, it's just black. There's no light scattering around. You get the really bright sun and that's it. Now, that's if it's during the day where the light's nice and scattering. At sunset, you're looking a long distance through the air. That blue light's all being scattered someplace else, so it's not making it to your eye. So instead, it looks reddish and yellowish, and the beauty of a sunset. Now, if you happen to have other stuff in the atmosphere, not just, say, air molecules, but dust particles, like, say, smoke from a fire, well, those are larger. They're probably still colloidal, so they're not gigantic. They're still kind of colloid size, but they could be suspension size. Those things will scatter light quite nicely, and they'll scatter light quite nicely at larger and larger wavelengths. And thus, the air doesn't look blue. It's not the pretty blue sky, it's more of a red or an orange, which is an absolutely creepy and disturbing image that thankfully I have not experienced firsthand. And I would like to keep it that way. Thank you very much. And of course, I mentioned there was a KXCD on this. And the classic question is, so why is the sky not purple? Two reasons. One, purple, like magenta, isn't actually a wavelength. It's one of those subjective experiences of red and blue. By the way, brown is in this category as well. That's kind of a cousin to orange, and that's your eyes trying to interpret intensity and light levels. Technology Connections did a beautiful video years ago on brown. The other issue we have is that the sun is not just dumping out all colors at the same intensity. The most intense colors are kind of in that yellowish greenish area, and so there's less blue light than there is yellow and green, and there's less in that dark near ultraviolet blue, what Newton would have called violet. Violet doesn't mean purple, it means dark blue. What Newton called blue, he actually meant more like cyan. Language evolves, interesting. Also, he just picked 7 because it sounded good. So there's no real clear why there's 7 colors in the rainbow. There's not. There's like the whole spectrum. It's just we slice and dice it 7 because Newton thought it sounded good. Also, our eyes are better at seeing closer to the cyan side of things than that far end. If you're in that violet, that deep dark blue, or that deep darkness would be the intensity of the light, but that deep blue color, well, you're at the edge of what your eyes can see, so it can't see it quite so well. And thus, the sky is going to be kind of that bluish, the sky blue color, because you're blending the quality of the scattering, as well as the amount of light coming in to start with, as well as your ability to see the colors. If you could see into the ultraviolet, it would look a little bit different. But of course we can't. Bugs can, we cannot. But with that said, I think I've covered everything. Have a wonderful day, and I will see you in future videos.